So in the next homework, we're going to be working on what are called optimization problems. And this video is just intended to introduce optimization problems, introduce the 5-step process for solving optimization problems, and kind of going over what the expectation is for the optimization problem homework. And then subsequent videos will show examples of solving different types of optimization problems. So an optimization problem is simply a problem in which we are interested in finding either the maximum or minimum value of an applied model over a contextual domain for the model. So here's how this plays into what we've already done. So in previous homework assignment, we did the extreme value theorem. And the extreme value theorem simply said, hey, if you have a function and it is continuous over a closed domain, so if I draw the picture of a function, give a closed domain, say from A to B, so we're working on the x-axis here. If we have a continuous function over a closed interval, then the extreme value theorem said, you're guaranteed that there's going to be a maximum and minimum value on the interval, and it may occur at critical values of the function, and it may occur at the function endpoints. So the extreme value theorem guaranteed for us the existence on a closed interval of a maximum or minimum value. So all we're going to do with an optimization problem is try to apply the extreme value theorem in addition to the first and second derivative test to identify maximum or minimum values for an applied model. So our function, instead of being a generic function of x, might be a volume function where we're trying to maximize or minimize a volume. So that's what an optimization problem is. Instead of worrying about a generic function f of x, we want an applied function or an applied model. I want to know a max or min volume. I have a height model and I want to know a maximum height or a minimum height. Or I have a profit function and I want to know a maximum or minimum profit. And I would like to use the tools from the previous homework assignments: extreme value theorem, first derivative test, second derivative test. We want to use the previous homework assignments and apply them to applied or contextual models. So there's going to be a process that we walk through as we solve these problems. In this process, I'm not going to include it on the slides when I do the worked examples. But you should take this down in your notes, and as I work through subsequent videos and work through optimization examples, you should look to see how I am following this process as we work through finding the optimized solution. So the first step in a solving an optimization problem is we want to draw an accurate picture of the situation, as always. That's one of the things that's been missing from the homeworks and gets marked down on exams. So you are expected to draw an accurate picture. It can't be floofy. So if it's a tree, I don't want to see a picture of a tree. You want to abstract it as a vertical line. So you draw an accurate picture that abstracts the problem. And then you want to identify, when you read the story problem that goes with the application problem, you want to identify every quantity or variable that's been given to you explicitly. Some things we're going to be just told. And then we want to find the variables or quantities that we need to determine. Maybe they've been given to us implicitly. It's implied that they're there rather than explicitly provided to us. So you draw a picture and you define all of the variables. And we don't use variable names like x and y when we're working with story problems or optimization problems. So we don't use x and y. You get marked down from that on exams. If it's a volume, use v. If it's an area, use a. If it's a length, use L. If it's a width, use W. If it's a height, use H. If it's a time, use little t. If it's temperature, use large T. So use variable names that make context in for the optimization problem. So draw a picture. So if it's a height model, draw the height model. Hey, here's height as a function of time. If it's a volume model, draw in the volume model that you're working with over your closed interval. So you want to try to find closed intervals so that you can use the extreme value theorem. So maybe it's volume as a function of width, height as a function of time, profit as a function of the number of items sold, N. So draw a picture and then name your variables, write down everything that you know before you start trying to work on things. Step 2, once you've drawn an accurate picture that abstracts the situation and you've identified any given, explicitly given quantities or implicitly given quantities, the next step is to find a primary equation for the variable or quantity that you're trying to optimize. The variable that you're trying to maximize or minimize, you need an equation for it. So for example, if it's volume and you have a rectangular cylinder, volume might be length times width times height. You're going to optimize some quantity. You need an equation for that quantity you're trying to optimize. If it's a height, you might need to use the height model, negative 16t squared if we're working in feet per second, plus initial velocity times time plus initial height. If it's a profit model, you might need to know revenue minus costs. You might have a revenue function and a cost function, and you need to take their difference to get the profit. But step 2 is going to be to find that primary equation that relates the quantity you're trying to optimize with the other quantities that you've been given in the story problem. Once you've written down the primary equation that you're trying to optimize, you want to check, is it a function of more than one variable? So if we have volume as a function of length, width, and height, well, in Calc 1, we're only working with single variable functions. Calc 1 is all about single variable calculus. So we've been using functions of x, where x is the only input variable. If we are working with a story problem, then our functions are functions of variables other than x, like length, width, height. But the idea is that the calculus we've learned so far has been predicated on our having functions of a single variable. So if, in step 3, if you see you have a function of more than one variable, you have to figure out a way to use ancillary or secondary equations, other relationships that you probably wrote down in step 2. How do you use ancillary or secondary equations to reduce your function to a function of a single variable? Maybe volume as a function of length, or volume as a function of height, or volume as a function of only width. So we need to take multivariable functions and describe them in terms of a single variable. That's going to be your step 3. Step 4, find a feasible, or what we've been calling in pre-calculus courses, a contextual domain for your model. You want to try to come up with a closed interval or a closed domain that your function needs to live over. So for example, if it's a height model, even it might be a downward opening parabola, and we know that parabolas go from negative infinity to infinity. But for our purposes in an optimization problem, this usually isn't going to be good enough. So we would want to recognize that a height model will start at time equals 0, and there will be some time, call it b, when the object's on the ground. So you do from 0 to b, the closed interval from 0 to b. So you identify that feasible domain where, for the story problem that I'm working with, where does my model actually live on the input or horizontal axis? And we want to find that closed domain so that we can use the extreme value theorem to guarantee for us that there's going to be a maximum or minimum value over that closed domain. Once we've done these steps, then we use calculus techniques and no other technique, because this course is a calculus course. So if you know some other algebraic mechanism for finding a max or min, you don't get to use it, because we're testing calculus techniques in this course. That's why the course is called calculus and not pre-calculus. So you use calculus techniques to determine the max or min over your closed feasible domain. And you want to use the tools from the last few homework assignments. So you're going to use things like the extreme value theorem to find that closed interval. Find your critical values on that closed interval, because the critical values are where relative maximums and minimums occur. But you know they're going to be global maximums or minimums possibly if we're working on a closed feasible domain. That's what the extreme value theorem guarantees for us. We're going to use things like the first and second derivative test, right? Concavity to determine whether the graph is concave up or concave down, which tells us whether we have a max or min. We'll use our knowledge of the geometry of functions to justify whether we have max or min. So for example, if you have a closed domain and a parabola opening downwards, if we have a parabola opening downwards, so it's concave down, and we have a closed feasible domain that we're working over, we could say, hey, because it's a parabola opening downwards, I know that if I have a critical number, it's going to correspond to a maximum. Or if I have a parabola opening upwards over some closed domain, I know that if I find the critical number, it's going to correspond to a minimum value, because it's going to be the vertex of a parabola opening upwards. So we're going to need to justify that we found a max or a min value. So that's generally what an optimization problem is. And we'll look through a series of examples of calculating max min values in the videos that are coming for this homework assignment.